In the early 1950s, American naval engineers became obsessed with a singular radical idea: the teardrop hull. They believed that if you stripped away the deck guns, the flat walkways, and the jagged conning towers, the parts of a submarine that make it act like a surface ship, you'd, at least in theory, have the most hydrodynamically efficient vessel ever built. But when they launched the USS Albacore to test this, they noticed something else. Without those blunt, jagged surfaces disrupting the water, the submarine wasn't just fast, it was strangely difficult for enemy hydrophones to hear. The Navy was onto something, but the acoustic math of the era just wasn't ready to help them. Fast forward to the height of the Cold War. Engineers dusting off captured World War II research stumbled upon a seemingly obscure German project called Albridge. It laid out the mathematical groundwork for calculating how sound waves interact with synthetic rubber. The Axis powers had tested it, shrugged at its high maintenance, and ultimately abandoned it. They didn't realize they had just handed the world the cheat code for acoustic invisibility. When Allied analysts fully decoded the physics behind the forgotten project, they realized the scientists had solved the unsolvable. They saw that while making a submarine completely silent was impossible, wrapping it in mathematically engineered materials and isolating its internal vibrations was finally within reach. This single realization moved submarine stealth from the realm of what if into the realm of hardware. It triggered the secret design revolution that transformed the deafening, clunky metal tubes of the 1940s into the smooth, haunting apex predators of the 21st century. Submarines that don't just hide in the dark, but effectively rewrite the laws of acoustics. Now, let's explore exactly what happened, how sonar and underwater stealth even work, and why this transforms our world today. The hype makes it sound like magic, like these subs have a magneto-hydrodynamic silent drive straight out of a sci-fi movie. But in engineering, there is no magic, only the clever exploitation of physical constants. To understand how we make a $3 billion steel Leviathan disappear, we have to stop looking at the submarine and start looking at its echo. Sonar was developed in the early 20th century and stands for sound navigation and ranging. Because electromagnetic waves like radar and light are instantly crushed and absorbed by dense seawater, navies have to rely on sound, which travels nearly 5 times faster in water than in air. Active sonar is fundamentally just a game of shout and listen. A ship sends out a massive pulse of acoustic energy, a ping. That pulse hits an object, bounces off, and a tiny fraction of that acoustic energy returns to the hydrophone. If you know how long the shout took to come back, you know how far away the target is. Simple, right? But the physics of that trip is where the stealth starts to happen. To understand why submarine stealth is so difficult, we have to build the math from the ground up. Let's derive the sonar equation. We start with our transmitter. It pumps out acoustic power, which we'll call source level. As that sound wave travels through the ocean, it spreads out in all directions, expanding like a giant sphere. Just by traveling through the water, the sound loses intense amounts of energy, a phenomenon engineers call transmission loss. Now, the acoustic energy hits the submarine, but the submarine isn't a perfect mirror. How much sound it intercepts and reflects back toward the enemy depends on its target strength. Think of target strength as the effective acoustic area the sub presents to the ping. This reflected sound now has to travel all the way back to the surface ship. Just like the outbound trip, this energy spreads out again, losing even more power. By the time it reaches the receiver, it has been subjected to spherical spreading twice, not to mention the energy simply absorbed by the salt water itself. Because sound weakens exponentially the further it travels, the physics of the ocean is already doing so much work to hide the submarine by swallowing up the signal. So why can we hear normal submarines at all? It comes down to 2 variables: target strength and the submarine's own self-radiated noise. While we can't change the laws of physics or the power of the enemy's sonar, we can change how much sound that submarine reflects and how much noise it makes in the first place. If we can make those numbers small enough, If we can turn the metallic echo into a dull thud, the crushing physics of the ocean will do the rest of the work for us, burying the sub in the background noise of the universe. But as we're about to see, reducing that echo is a lot harder than just turning off the engine. Now, back to the story. Acousticians soon realized that a submarine is basically a giant metal drum. Every pump, every gear, and every dropped wrench creates mechanical vibrations that travel through the steel hull and radiate perfectly into the ocean. If you want to be invisible, you have to master mechanical decoupling. By the 1970s, engineers hit a wall. You can't just put a nuclear reactor on a ship and expect it to be quiet. So they proposed a radical workaround: rafting. Instead of bolting the engines to the floor, they mounted the entire engine room on massive, mathematically tuned rubber shock absorbers. They decoupled the machinery from the hull. But what about the enemy's active sonar pings? To solve that, they brought back the World War II cheat code: anechoic tiles. They covered the entire outside of the submarine in thousands of rubber tiles, each injected with microscopic air voids mathematically sized to trap and absorb the exact frequencies of enemy sonar. They turned a nightmare of acoustic physics into a simple game of mechanical isolation. On sonar, a 7,000-ton titanium attack sub suddenly possessed the acoustic signature of a small school of fish. As supercomputing power scaled, engineers at Electric Boat and BAE Systems could finally move onward. They began using high-fidelity fluid dynamics solvers to tackle the loudest part of the submarine, the propeller. When a standard propeller spins too fast, it creates areas of low pressure that literally boil the water, creating tiny bubbles that instantly collapse with a deafening popping sound. This is called cavitation, and to a sonar operator, it sounds like an underwater explosion. Using advanced computers, engineers designed highly classified pump jet propulsors. Instead of exposed blades, they housed heavily curved asymmetrical rotors inside a hydrodynamic shroud, choreographing the flow of water so precisely that cavitation was essentially eliminated. The result was the Seawolf and Virginia-class submarines. On these subs, every valve, every pipe, and every inch of the hull is engineered to ensure sound doesn't escape. But even modern nuclear submarines have issues. For one, they are wildly expensive, costing upwards of $3 billion each. Furthermore, a nuclear reactor generates massive amounts of heat, meaning cooling pumps must be running 24/7, 365 days a year. A nuclear submarine can never truly be turned off. In total, they are a masterclass in physics, but a nightmare in operational limits. Now fast forward another 30 years to the 21st century. Navies around the world decided a modern alternative was needed. That's where air-independent propulsion, or AIP submarines, come in. If the nuclear submarine was the proof that we can dampen acoustic physics, the modern AIP diesel-electric sub, like Sweden's Gotland class or Germany's Type 12, is the proof that we can perfect it. Modern high-fidelity battery tech and fuel cells allow these submarines to operate underwater for weeks without a nuclear reactor. Because they don't need constant cooling pumps, they can shut down completely. They don't just dampen noise, they sit on the ocean floor in absolute, terrifying silence. With AI and digital acoustic warfare baked into every corner, they represent the new vanguard of naval warfare. But the Americans and their allies aren't the only ones. The physics we've discussed, spherical spreading, transmission loss, and acoustic decoupling, they aren't just Western secrets anymore. They are universal constants, and the rest of the world has been paying attention. We see these same fundamental laws applied in the anechoic coatings of the Russian Yasen class, the advanced pump jets of the Chinese Type 039A, and the massive unmanned underwater drone fleets currently being developed globally for the next generation of naval combat. And with AI and digital warfare on the rise, it seems increasingly likely that the deep ocean will be the ultimate frontier of modern defense strategies. It's truly a strange shift in history. The story of submarine stealth has evolved from an abandoned rubber coating in a World War II yardage into a high-stakes, multi-billion-dollar global competition of acoustic optimization. and that gives us a unique new perspective on what the battles of the future will sound like.